So here we go. We are recording. So let's take a look at the first question that they provided us. And I'll hang it up here so we can see it. This is definitely not the optimal way of dealing with this. I could show you the screen or something, but I'm not doing that because I'm too old. I don't know if that's a good justification. But anywho, so let's take a look. Getting a little closer. Just a little bit closer now. All right, here we go. Good. So just looking at the situation, we see a cart that is on a roller coaster, and they have the track here, and they say it's a parabola first, and then down here, this turns into a semicircle. Okay. So far, so good. I think this is a good indication of what they're probably going to do, and I tried to replicate that on the exam that you guys just took. That interpreting a diagram, interpreting a graph, something that's not really Googleable, I know is going to be big on the list of things that you should be expecting. Okay, so they've got a cart and they are asking about different positions in that process. Okay, and they have, by the way, not just to make fun of them for a second, I don't know if you've looked at this. Can you actually see it on the screen, or is it too small?
I think they're too small.
It's kind of small?
It's too blurry for me.
Oh, yeah.
So that's kind of the shape. And they've got this is spot A. They've got a little cart here. Is that better? Is that showing up?
Are the other points on it just B, C, and D, or?
Yeah, I'll label them. So they've got point B here. They've got point C there, and they've got point D down here. Okay, that better? Is that visible now?
Yep.
Okay, good. I don't know how your physical intuition is. Is your physical intuition looking at this the same as mine? Because I'm thinking if this cart goes, what's going to happen somewhere around point B?
It'll fly off the track.
It'll just fly off. Like, come on, people. This is not going to retain contact. It looks like it's just going to go, you know, and you're going to fly and hit the ground here, and there'll be a tremendous crash, and there'll be like wheels all over the place. But oh well, they're trying hard, so we shouldn't make fun of them.
No, it
trying to
says
make
that
this.
it's fitted with wheels so that it can't come off the track.
Yeah.
Oh, is it really?
Yeah.
Oh, those rascals. Okay, good. Well, thank you for giving us that, because I'm sure they were like, that thing is going to fly off. Okay, so fine, it doesn't fly off, and they're asking us questions about this. Okay, so let's take a look at what they're saying, and specifically, they're asking for the acceleration that this car would experience at points B, C, and D. So, oh, sorry, accelerations at point A and D. So A, it starts from rest, okay? So if it starts from rest, that means, and this is the key thing here, if it's not moving, what acceleration do we not have to worry about? Okay, based on your silence, let's go back and remind ourselves that, ooh, shiitake, this is garbage. Actually, I thought this one was working. So no, so here we go. This is the working red one. These Schneider ones are actually way better than the ones I got first. So just for future reference. So acceleration comes in two, whoa, crap, it's fine. Acceleration comes in two flavors. What are the two flavors of acceleration?
Speed changing and direction changing.
Good. So it's speed. I'm just going to do delta, because that still shows up. I'm going to back this up just a shnook. There we go. So there's a speed change, and then the other one. How many red ones do I have? A lot. This is actually my new one, I think. Yeah, there we go. So we have direction change. And for the direction changing, yes, we have an equation for that. Direction changing, also known as centripetal acceleration, right?
V squared over R.
V squared over R, exactly. So that's V squared over R. So that direction changing acceleration, that centripetal acceleration, when V is zero. That makes sense?
Mhm.
So when we have a point like point A, where we're not moving, right? We don't have to worry about the fact that there is centripetal acceleration. So again, we can separate our acceleration into a direction changing, which is always perpendicular to the motion, and speed changing, which is in the direction of motion. So this cart's going to start moving in this direction, and that speed changing acceleration is there. But because there is no centripetal acceleration, we can ignore that. Not ignore that, but leave it off. So that is the total acceleration, which is only speed changing acceleration. Does that make sense?
Yeah.
Okay, good. Now, that was point A. Righty. Okay, now at point C, and then they ask about, do they ask for point D as well? Let me see.
Yeah, they asked for point A and
Okay,
D.
let's they asked for A, C, and D. Let's actually answer
A and D.
A and D.
Yeah.
State the direction at points A and D. Okay, good. So, super. Okay, so at the bottom, so here we are at the bottom, and we're moving at the bottom, and we always use that super scientific process of indicating that by using kind of little, it doesn't show up at all. There we go. There we go. It's moving. And at this point, it's between the down and up parts of the track. As it was going down, it was speeding up or slowing down. So as it was going down, it's speeding up or slowing down?
Speeding up.
Speeding up.
Speeding up. And then as it's going up, it's speeding up or slowing down?
Slow down.
Slowing down. So it's switching from speeding up to slowing down. So right at the bottom, is it speeding up, slowing down, or neither?
Neither.
Neither. So at the bottom, there is no speed changing acceleration. It's not getting faster or slower. So the only acceleration at this point is direction changing. Make sense?
Mm-hmm.
Okay. So that means we need to have an acceleration towards what?
The center.
The center of the motion. So that means at the bottom, the acceleration is here, right? And it's purely centripetal. Make sense?
Mm-hmm.
Okay. Am I doing something that's super easy, or is this helpful?
Helpful.
Helpful.
Yes,
Okay, good. Good. And just for kicks, do they ask about point B or C?
Yeah, next question. They
State the
ask
forces
about
acting on the
forces.
organism and state the direction of each force. Okay. So if we're in between, so actually I'm going to go, this is too tight at this point. So I'm going to go underneath and we say, okay, we have this track, right? And now we're looking at a point like this, somewhere there. It doesn't really matter exactly where it is, right? And now we're moving. Good. And they don't tell us to put in the acceleration direction, but tell me the direction of the acceleration of this cart. And what I'm going to ask you is basically to orient. This would be a good thing to do for them on the AP exam, because they might say, imagine you have a coordinate system here, and this is the X direction, and this is the Y direction. Tell me the direction of the acceleration at this point.
Well,
Is it-
it's mainly towards. Yeah. Oh,
Okay, Sam, I think that was you. Please say what you're saying.
I thought I heard someone else. Okay. I was gonna say it's mainly towards the X direction, but a little. It's going up a little bit.
Okay, so if I was going to go nerdy on you and say, is it in quadrant 1, 2, 3, or 4, or is it on an
Quadrant one.
axis? quadrant 1, okay? So because it's speeding up at this point because we're still going downhill, right? But it's also accelerating towards the center of the motion, which is up here. So we would expect, hang on, it's a little lower actually. So it's kind of in this part, it is on the circular part. So it is curving, that's important, this direction. So that means the direction of this would be in this direction. Acceleration is in that direction. Okay, that makes sense? It's important to realize that we are on the circle like this at this point. And that's why they have it a little lower. I drew it a little too high, sorry about that. But we are going in a circle like this. So there is centripetal acceleration, there's speeding up acceleration. So the net acceleration is going to be pointing into quadrant 1. Okay, good. And oh yeah, now how's that possible? What forces are contributing to generate this acceleration? So they're saying there's no air resistance, there's no friction, I think, in the problem. So what are the only forces we have that can contribute to this?
Normal force,
Yep, normal force is going to be in this direction.
gravity.
Oh, crap. So it is important to remember that normal force is always perpendicular to the surface. And then we also have a gravitational force is going to be obviously straight down. There we go. Now, I drew in in this direction. It is important that if you are required to make a drawing, which I don't think will happen, that you don't put the acceleration on the free body diagram. Just a reminder about that because they really, really, really don't like that. I'm going to kind of pull it off the object a little bit and say, we're just indicating the direction of the acceleration. We're not actually saying that's a force because they tend to accuse you of thinking acceleration is a force. It's obviously not. Okay, makes sense?
Mhm.
Good. So there's question A, B, and C. Determines that the car takes 10 seconds to go from point A to point D. So we say, okay, to get from here to here, at the top we're here at t equals 0, and down here we're at t equals 10 seconds. Okay, fine. That's nice to know. And they say the distance from point A to B is 100 meters. Distance from point B to D is also 100 meters. The students also know that the car is located at point A at time t equals 0, at point B at time 5, and point D at time, okay, all right. So this is 5, and then here we're at 0, here we're at 200, and here we're at 100.
Okay, is that like a direct line, a length of a direct line from point A to B, or is that along the track?
At that, they're going to, they do not clarify this, but it's along the track. I don't think they clarified properly. It's a good question, but the length of the track, they should have said something like the length of track or along the track. And I don't think they say that, but that's implied in the question. Okay.
Okay.
So we've just stated that, and let's see what we got here. All right, we stated it all. The student hasn't taken AP Physics. Well, why are they talking about this? They shouldn't be doing this problem, but oh well. And doesn't know how to solve the problem exactly. So instead, they suggest that the distance x traveled by the car can be modeled by the function x equals 6t squared minus 0.4t to the cubed, where x is the distance. A graph representing the suggested equation x of t is shown below. Okay, they give us a graph. There we go. And if you're looking at it right now, that's great. And if not, here's the graph. Good. So we have a graph, and it meets the requirements that we have that it starts at t equals 0, x equals 0. At 5 seconds, it's 100 meters. And at 10 seconds, it's at 200 meters. Okay, makes sense. And okay, good. A second student agrees that from t equals 0 to t equals 5, the graph could correctly model the motion of the car. Identify at least 2 features in the graph that are consistent with the behavior that a car must have as it travels over the track described. Okay, so let's take a look at the graph and try to think about that. stick that over here. And scooch this over. There we go. All right, so I'm going to do the same thing I just did, which is to kind of redraw the line to make it a little thicker so it's easier for you to see. Okay, there we go. And they're saying from 0 to 5 seconds, okay? This is agreeing with what they would expect based on this graph. Now, looking at the graph here, what agrees or disagrees? Hang on, they asked first of all to see what agrees. Okay, so could correctly model the motion of the card in the first 5 seconds. Okay, I think it can't, but that's just me. I think there's a mistake here, but whatevs, because there's a problem. But how does this agree with what we see in the picture from A to B?
That at t equals 0, it's at 0, and at t equals 5, it's at 100 meters.
Good. So the position and time is correct. So it's definitely true that these 2 points are correct. So it's matching up those 2 positions. Okay, so 0 and 5 and 0 and 100 match up. And what else matches up? If you think about the process of the cart coming down here, what should be true? What should be true of the acceleration of the cart?
It's concave up.
It's concave up, so that means the acceleration is
In the
Positive.
direction of motion.
positive. Okay, second derivative is positive. Okay, you can enter it that way if you want to. So that's true. I think those 2 facts would match up, and I think they're probably looking for those 2. That it's true at 0, it's at 0, at 5, it's 100, and the acceleration is increasing. However, looking at the diagram where A is placed, what should be the initial acceleration according to this diagram? 0 or not 0?
Not 0.
Not 0. And think about it. If it was 0, it ain't moving. It's not going to get moving because it's placed at rest here, isn't it? I'm not sure. Anyway, if you placed it here, it wouldn't work because if you placed it here and acceleration was 0 and V was 0, it would never start moving. So that's kind of a problem. Make sense?
Mhm.
Wouldn't it start moving due to gravity? Because
Yeah, I know it would be, but it just doesn't look right here. It doesn't look, I don't know, maybe it's wrong. Maybe
Well, it
it's
could be just very small.
It could be. You're right. It could be the acceleration is actually non-zero. Anyway, but the 2 matching things for sure is 0 to 5, 0 to 100 works, and the acceleration is increasing. Good. Okay. Now, they're looking at then the process from 5 to 10. We're almost done. We only have 3 minutes, but I think we can answer that question here, which says the second student disagrees with the model for the time from t equals 5 to t equals 10. Identify features in the model, equation, and or graph that are inconsistent with the behavior that a car would have on this track. Explain how the graph does not correctly model the motion of the car during the second 5 seconds. So we're looking from B to D here. And let's think about this. Okay, so features in the model, equation, and or graph that are inconsistent with the behavior that a car would have on this track. Okay, let's see. Let's look at the diagram. What's about the graph? What's going on there?
Well, the graph is concave down, even though it still should be accelerating.
Speeding up.
It should still be speeding up, right? The acceleration is still down the track, and therefore it is not correct. So the acceleration is actually negative, right? So it's slowing down on the graph, so that's not right. Okay, that's correct. That's wrong. What else is wrong? They say, is there something else? Did they say 2 things, or did they just say features? Okay, so that's not good. The model does not work because it should be accelerating and it's not. Anything else you guys see? I don't see anything either. Hey, Eric. Do you show up too? No. All right.
Well, maybe. Oh, wait, sorry.
Yeah.
Maybe another thing could be that at time is equal to at t equals 10,
Yeah.
it looks like the slope is 0, even though the speed should not be 0.
Okay, good. That's good. That's actually really good. So here v would be equal to 0, and it's not. And here a is smaller than 0, and it's not. And that you can't read that even because I wrote it with a pen, and sorry about that. I'll write it with this thing over here. So it's true that a is not smaller than 0. And up here, it's not true that v is equal to 0. So both those are correct. And we're at the end of the time, and I will stop it here.